How's the religion?
Good, and yourself.
Yeah, I can't complain, man. I'm trying.
We're doing science today.
Yeah, today we're doing science. Uh, so we're gonna start from the end. Like last time. Last time I think we did a bit of other chapters, right? So we're gonna start with chapters that we didn't even touch last block. So we're gonna start with heat. Okay. So I don't know if maybe you can give us the definition of heat. What is heat?
Uh, from my from my understanding, it's I would say it's one of the elements of Earth that when acting on a surface or an object, if it's like now a metal object, like let's say now like a railway line, if there's enough heat to overcome a certain level, and then the railway will expand a little bit.
Okay, so is it fine if we define as for example you can say heat is a what is a source of energy.
Yes.
Okay. So once you're saying heat is a source of energy, what we're going to look at today, the first thing that we're going to look at today is going to be linear expansion. There's going to be linear expansion. So when you talk about linear expansion, it's nothing. You're just talking about the expanding of things in a linear motion, right? For example, let's say like what you said. Let's say, for example, we're having this metal thing here. Then we say this thing is it's having this as the original length, which is going to be our length original, right? Then we're going to heat up this thing. So when we heat up, basically we're going to find out that we are heating the elements of this thing. So when we heat it up, it's going to increase its length.
Yes.
So when it increases its length here, this part is the one that we're calling the what? Our change in length. This is the change in what? In length, right? So we know that linear expansion is given by linear expansion, which is change in length, right? So it's going to be we're going to say that change in length here is equals to the length original multiplied by the coefficient of friction multiplied by what? Change in temperature. So the change in temperature here, we are just simply saying that change in temperature is equals to T2 minus what? T1, which is the same as saying T final minus what? T initial. Okay? So to get now the final length right now is going to be now final length, which is length final is equivalent to the change in length plus what original no, it's not, it's written like plus original length like this. Okay, do you have any question on this one?
Tatenda, I just wanted to confirm quickly with you. Are you recording the classes like last time?
Yes, I'm recording them as well. Let me just check here if I'm recording this one. Yeah, I'm recording them. I'll send them to the group chat. I think by end of today I'll send them.
Did I miss anything? Hi guys, how are
Ah,
you?
we're just starting.
No, okay.
All right. So from this part, do you have any question on this part?
Can you just maybe repeat the thing that I missed at the end? Sorry, man.
No, it is the first, like everything which is on this part. It's everything that I've done. So we are saying heat, which is we can just define it as a source of energy. So the first chapter that we're going to be looking at under heat is linear expansion. So when you talk about linear expansion, we're saying if ever we heat up an object, a metal bar specifically, that metal bar is going to expand, right? So when it expands, it's going to be having the certain change in length, which is this thing that I've labeled here, this part. Yeah. So now to get this change in length, we're going to be using this formula of what's saying the change in length is equals to the original length multiplied by coefficient of friction. So the coefficient of linear expansion multiplied by what? Change in temperature, of which you know that the change in temperature is equals to final temperature minus what? The initial temperature. So now we're saying the final length is going to be length, the change in length plus the what? The original length. Okay. Then we also have another formula which is we're going to say that coefficient of expansion, coefficient of expansion, which is known as this thing, is equivalent to the change in length over length original. So we are saying this one, you see delta L representing the change in length, then over the original length. Okay. So this is it from the what they call it, in expansion. So we just want to look for an equation here that I'm having. I'm having a single equation. Let me just check from here. So here they're saying, we're having a question, they're saying a cast iron rod is 5 meters long and is heated from 10 degrees Celsius to 150 degrees Celsius. The linear expansion coefficient of cast iron is 6.28 times 10 to the power negative 6 degrees Celsius. So here they're saying determine the expansion that takes place as a result of heating up. So and also calculate the final length. So here they want us to calculate the what? The final length. Okay. So we know that the formula for calculating the final length, we use this formula which says final length, which is L final, is equals to length original plus what? Change in length, isn't it? So now, anyone who still remembers the formula for change in length?
Length times coefficient of times changing. Is it the changing? What is?
Changing temperature, right?
Changing temperature, sure.
Okay, so what is our original length? They're saying the cast iron is 5 meters long. So this is going to be what? 5 multiplied by The linear coefficient of expansion was what? 6,28 times 10 to the power of what? Negative 6 multiplied by. What is our change in temperature, Mr. Lishin?
It's the 150 minus the 10, so it's 140.
Yeah, so you also have to check here, right? If this is kelvins per Kelvin, it means that you have to change your temperatures to what? To kelvins. But now, since it's degrees Celsius, just gonna use this as degrees Celsius, then we're gonna say 150 minus 10. How much do you get here if you punch your calculators?
I get 0,004.
Okay. Can you press engineering so that you can get something like times 10 to the power something? How much do you get?
If I move the comma, then it's gonna be 4.3 times 10 to the power 3.
All right, negative 3, sorry. So it's gonna be 4.396 times 10 to the power of negative 3 millimeters. That's what I got. Sorry, meters. If you punch this one, you get this one. So meaning that your change, your final length, which is length final, will be equal to 4,396 times 10 to the power of negative 3 plus 5. Then that's going to give you 5.004396 meters. Is it difficult, guys?
So far, not yet.
All right. So let's move on to the next part. Can I erase this part?
Not yet.
Sure.
I'm still writing quickly.
All right. You just let me know when you're done, then I can erase.
So which question, which example is this from, Taten?
Here I'm using J. Olivia. It's a textbook.
Oh, okay, cool.
Mm.
So it's not the same. It's not the same textbook that you're using, Mus, or are they the same?
Which one are you using?
MJJ van Rensburg.
No, that one is too complicated. That one will make you to fail. It will make you fail. That one. So it's better if you just write down the notes that I'll be giving you here. Then you just use that one for reference purposes. When I get time, I'll scan this one. Then I'll send it to you guys.
Okay, let me just write the question.
Yeah. When you're done, just let me know. Then we can move on.
Addenda.
Yeah.
Does each material have its own coefficient of expansion?
Each material has its own. So you see that when you're writing exams, I'll show you when we are done with this chapter. Every question paper it will be having all the what they call it, coefficient of friction of different materials. We have cast iron, we have gold, we have steel, and everything.
Can continue. I don't know if Lucian is finished or Lucian, are you done?
Now I'm done. I'm waiting on you.
No, I'm finished, my man. Sorry.
Let's move on. I'm just gonna flip this page and go to the next one. Now let's talk about another interesting chapter or interesting subheading, which is going to be area expansion. So here we're having what? Area expansion. So what's gonna happen here? For example, let's say we're having a cube like this, right? Okay. So this cube is going to be having its length and its what? Its width, isn't it? If we heat up this thing, what's gonna happen is that it's going to increase in all the directions, but in this case, I'm just gonna take it as if it's gonna increase in one direction. So it's gonna increase like this. But in general terms, we're saying it has increased the juice towards this direction, and what this direction as well as this direction. But what we have done here is that we took the change from this side, we put it this side, from this going up, we put it at the bottom. So now we're going to be having this what change in length here, right? And also change in what?
Width.
In width. Okay. So we know that, guys, for us to calculate area, right? We know that area is equals to what? Length times width again of this object. So this is for the what? For the square. So now if we are calculating change in area now, change in area is going to be now change in area is equivalent to original area multiplied by 2 coefficients of what? Friction multiplied by change in temperature. Can someone now try to explain to us why are we using 2 coefficients of frictions here?
Because we have two sides, length and width.
Thank you. Because we have 2 sides. So now you find out that this area can be written now as area original multiplied by beta multiplied by what? Change in temperature. Okay, so here, guys, make sure that when you're writing signs, right, you don't forget that sometimes they'll say calculate beta or calculate the coefficient of area expansion. So the coefficient of area expansion, right, area expansion is given by 2 multiplied by what? Alpha. And what is alpha again? It's coefficient of linear expansion. So now we're saying basically we're going to be using this formula here. But now if we want to get the total change in area now, we're going to get the final area, which is equals to area final. It will be equal to area original plus change in what? Area. Okay. May you copy down these formulas as well?
So if it's like this, then if you're saying two coefficient of linear expansion, are you gonna give in only one coefficient of friction, coefficient of linear expansion? Sorry.
Because remember, okay, so like when you talk about area, right? Area, we're talking about a material. Let's say, for example, you're dealing with a brass, right? So we are saying
Sure.
whatever that you're having, if we're having a cube of brass, it's one material. So they won't give you two different linear expansions. They'll give you the linear expansion of brass. But now, you know that this brass is going to be having a length and a width. And in both directions, we're having coefficients of what? Linear expansion. That's why we multiply the coefficients of linear expansion by 2 because we are considering two sides.
Okay, sure. Can continue. Oh.
Okay, Lishin, you good?
Yes, I'm good.
Okay. They are saying here a brass plate is the following. Yes, the following dimensions. 400 by 300 millimeters at 12 degrees Celsius. Calculate the area of the plate at 100 degrees Celsius if the linear coefficient of expansion linear expansion coefficient of expansion Okay, so you're saying a brass plate has the following dimensions, right? So you're saying you're having something like this. Whereby we're saying this can be 400 by what? By 300 millimeters, and this is going to be millimeters as well. So basically, this is our plate. So we want to calculate the area of the plate at 100 degrees. So you can see that if we're saying calculate the area it means that's the final area, isn't it? So what you have to know is that final area, let me just remove this WhatsApp here. Just remove it. Where is it? Check here. So we know that area final is equals to area original plus change in what? In area, right? So first of all, we have to get the change in area. So we know that the change in area is equals to area original multiplied by 2 coefficient of friction multiplied by what? Change in temperature. Okay, so here guys, they gave us these dimensions, right? So I honestly like to use small numbers, so I'm going to use this one as meters. So I'm going to convert 400 and 300 to meters. So this is going to be 0,4 multiplying 0,3 multiplying 2 multiplying 0.123419 multiplying open bracket. Changing temperature is going to be 100 minus 12. Okay, how much do you get if you punch your calculators, guys?
$401.28.
That's gonna be 401.28.
0.28 times 10 to the power of negative 6.
So this is going to be square meters, right?
So
But now we need final area. So it's going to be final area is equals to what? 4.01. 401.28 times 10 to the power of negative 6 plus open bracket 0,4 multiplying what? 0,3, because that's our original area, isn't it? So how much do we get for our final area here?
$0.1204.
0.1204. It doesn't have times again. Okay, square meters. Any question on this one? Okay, you can copy this one, then we do the second example, then we move on.
Tatenda. I don't know, young. My calculator. When I punch in the final area, I get 0,741.
Did you put like did you get 4.4 or 1.28 times 10 to the power negative 6?
Yes, that I got.
Then just say plus open bracket, then 0,4 multiplied by 0,3, close the bracket.
Okay, no, it was the plus. I put the plus sign instead of a multiplication sign in the brackets.
All right.
So now we have covered linear expansion and area expansion.
Yes.
So basically the questions are gonna be asked like the way that like the example that we did now.
Yeah. It might just change it a bit. For example, okay, we're gonna do another one right now, and you see how they might change. You know, like these guys, they just try to change a little bit of things.
I don't think we can continue. I think Lishan, are we done?
Yes, I'm done.
All right. Let's have this other question. This one is a bit complicated. They are saying a steel plate here's an area of 2,4 square meters at 2 degrees Celsius. It must be enlarged and must be enlarged to 2,43 square meters. If still here's an area expansion coefficient of 1,5 times 10 to the power of -5 per degrees Celsius. Calculate to what temperature the plate must be heated to achieve the new area. Okay, so at first you're saying you're having this, right? Our area is equivalent to what? To 2,4 square meters, and we are saying our temperature here is equivalent to 2 degrees Celsius, right? So we're going to heat this up here. When we heat it up, we need it to go to area of 2,43 square meters, right? And temperature here it's unknown, isn't it? So here we are saying we're having our linear area. So this is area now, guys. You can see that they gave us as area. So it's no longer this, but it's now what? Beta, which is equals to what? 1,5 times 10 to the power of -5. Okay. So here we want to understand to what temperature the plate must be heated, right? So we know that final area, right, is equals to what? Change area plus what? Original plus area original. So if we can if this one, we can say our final area minus our area original is equals to what? Change in what? Area. Meaning that our final area minus area original is equals to what? A original multiplied by beta multiplied by what? T2 minus T1. This is change in temperature basically. This is our what? Change in temperature. And you know that this is our what? 2 alpha. So now our area final was what? 2,43 minus 2,4, right, is supposed to be equal to our original area is 2,4 multiplied by 1,5 times 10 raised negative 5, open bracket, T2 minus what? 2. Here we are going to get 0, how much do you get here if you punch your calculators? 2,43 minus 2,4.
0.03.
0,03, right, is equals to 2,4 multiplied by 1,5 times 10 to the power of negative 5. How much do you get?
I get 36 multiplied by 10 to the power negative 6.
Okay, so this is gonna be 36 times 10 to the power of negative 6, right? Open bracket, T2 minus 2, all right? So now what we're gonna do is that we're going to divide everything by 36 times 10 to the power of negative 6, right? Here we divide by 36 times 10 to the power of negative 6. So this one cancels this one. 0,03 divided by 36 times 10 to the power of negative 6. How much do we get?
I get 833,33.
833, what? 33 is equals to what? T2 minus 2. So this is a negative sign. If it jumps, the equal sign becomes positive. So that's 833, 33 plus 2 is equals to what? T2. Meaning that our T2 will be equal to what? 835, 33 degrees Celsius. So we are supposed to heat up our object up to 835, 33 degrees Celsius. Is it complicated or confusing?
No.
All right.
Yeah. Will we only be working with like with squared objects, or will they change it to like triangles or?
Yeah, they might change it to triangle, but the concept still remain the same. Just first of all, calculate the area of that thing that you are working with. If it's a triangle, calculate the area of the triangle. If it's a rectangle, calculate the area of the rectangle. If it's a sphere, calculate the area of the sphere. But the procedures and the steps are the same. Okay, so you can just copy this one, then we can move on.
I'm done. We can just wait 20 seconds. So.
All right.
What I'm still busy, I'll tell you now.
Okay.
Sure.
Okay. Okay, let's move on. We're going to talk about now volume expansions. So when we talk about volume expansion, guys, we have Jesus. I'm gonna call, what do you call this thing, guys? Now I call it gamma. This thing, it's like this. I call it gamma. So we're saying gamma is equivalent to the what? That's what we call the coefficient of volumetric expansion. Okay, so here we're gonna have something like, for example, we know that this is equivalent to 3 times coefficient of what? Linear expansion. So the change in volume will be equivalent to now volume original multiplied by 3, coefficient of friction multiplied by change in temperature, coefficient of linear expansion, sorry, which is equivalent also to volume original multiplied by gamma multiplied by change in what? Temperature. This is the what? The formula. Maybe just copy it down, then we can find an equation that we can do on this one. When you're done, let me know so that we can move on.
Sure. I don't know if Lishan is still busy.
I'm done.
Done? All right. So here they're saying calculate the increase of 100 cubic millimeters mercury at 20 degrees Celsius when heated to a temperature of 45 degrees Celsius. Calculate the overflow of mercury. The overflow of mercury in 100 cubic meter flask that is full. Well, this question. That is full at 20 degrees Celsius and is heated to 45 degrees Celsius. The linear expansion coefficient. The linear expansion coefficient. It was on the screen. The linear expansion coefficient of mercury is 6 times 10 to the power of -5 per degree Celsius, and that of glass is 9 times 10 of -6 per degree Celsius. Calculate the increase of 100 cubic meters mercury at 20 degrees Celsius when heated to a temperature of 45 degrees Celsius, right? Calculate the area overflow of mercury in 100 cubic millimeters flask that is full at 20 degrees Celsius and is heated to 45. The linear coefficient of mercury is this one and of glass this one. So we're having two things, right? So what we're going to do here, we're going to calculate them as two. What we're going to do, we're having two different things, so we're not going to combine them. So we're saying this is going to be for mercury on its own. So this is basically for mercury, and this is going to be for what? For the glass, okay? So we are saying the change in volume of mercury, right? Change in volume of mercury will be equal to volume original multiplied by gamma multiplied by change in what? Temperature, which is the same as saying volume original multiplied by 3 coefficient of expansion multiplied by what? Change in temperature, which is going to be, our original volume was what? 100, so it's going to be now 100 multiplied by 3. The reason we're using 3 is because they give us the linear, it's not the volumetric, it's saying linear here. So that's 3 multiplied by 6 times 10 -5.
So, Katenda, if it's
multiplied
linear,
by-
meaning, sorry, Katenda.
Yeah.
So if they're saying 3, so meaning it's length, breadth, and height, or
Yeah. If it's linear, it means that okay, we're having something like this. Okay, so we know that this is the breadth, right? I'm lying. This is our width, this is the breadth, and this is our length, right? So we are saying we're having 3 different things. So here we are having linear coefficient of expansion towards direction. We're having also coefficient of linear expansion towards direction, and they're also having another coefficient of linear expansion towards direction. So all of them are 3. That's why we are multiplying them.
Sure.
Yeah. So, but if they mention that this is volumetric expansion coefficient, we don't have to multiply by 3 because they already multiplied it. So this is going to be 100 multiplied by 3 by 6 times 10 to the power of negative 5, open bracket. This is going to be 45 minus 20. How much you get here?
0.45.
0.45. So this is gonna be now 0.45 cubic what?
Did Dishan get the same
meters.
answer?
Mr. Lucian?
No, it doesn't seem so. Okay, no, yes. If I put it in brackets, then I get 0.45.
Let's go to the class. We're going to say change in volume is equals to V original multiplied by omega multiplied by change in what? Temperature, like this. Okay, let me just answer. I don't know why the college is calling me. Let me just answer. Okay, so here we are now saying our original volume for calculate is still the same, isn't it? It's 100 multiplied by, but now we're having mercury, which is what?
9 times 10 to the power of negative.
Sorry,
The
class is
glass.
9, right? So that's gonna be 9 times 10 to the power of negative 6 multiplied by 45 minus 20. How much do you get here?
I get 0.0225.
That's gonna be 0.0225 millimeters squared. So calculate the overflow. Overflow here, guys, is gonna be overflow.
Why is this one squared and the previous one is cubed?
Hey, sorry, it's cubed, guys. Thank you very much. Because it's volume. So overflow will be equal to 0.45 minus 0.0225. How much do you get?
I get 0.4275.
0.4275 cubic meters. Just like that. Okay, any question?
No.
Okay, so let's just copy this and we move on.
I've already copied mine.
This side also.
Okay, then is this also done?
Yes, I'm done copying it then.
Okay,
We can carry on.
If we move on, we are going to go to the gas laws now. But before we move on, I just want us to have a comparison here so that you don't get confused when you're writing these questions. Okay, so here the first one is going to be linear expansion. Then we have area expansion. Then the last one is volume. Volumetric expansion. Okay, so here we are saying linear expansion, alpha is equals to alpha, right? Area expansion, alpha, linear expansion coefficient. So alpha is equals to alpha. Here we have area expansion, beta will be equal to what? 2 alpha. Here we are going to have gamma, which is equals to 3 alpha. Okay, so if you just understand this part, guys, I think it's going to be very, very easy for you to understand the chapter. So let's move on to gas laws. Okay. So we have the first thing that we're going to look at today is going to be the expansion of gases. So we're going to have the expansion of gases. Okay. So under the expansion of gases, we have a variety of things. We're going to look at the Boyle's law. Okay, let me remove this one. Don't need it that much here. Let me just start by going to the law of Boyle. Which is called constant temperature law. Okay, so here we are saying that Boyle's law states that the volume of a given mass of gas is inversely proportional to the pressure upon it. If the temperature is kept constant. So now we're having this and this. This is going to be our PV diagram, pressure and volume. Then we are saying we have this. So we're saying here pressure volume is equals to what? Constant. What does it mean? It means that P1 is equals to what? P2. Okay. Then we have the second one, which is the law of Charles. Here it says that, which is sometimes known as constant pressure theorem. So this one is said to be the volume of a given mass of gas, of a given mass of gas kept at a constant pressure is directly proportional to the absolute temperature. Meaning that V1 over T1 is equals to V2 of what? T2. This thing is represented on a PV diagram like this. This is pressure, this is volume. Okay. Are you done copying so that you can just try to do one example? Then we can move on to the last part, which is the gas characteristic equation, when we are done with it.
I'm up to date with the copying.
Okay.
Just give me a minute.
All right.
So we can continue.
All right. So let's just write down the question. We're saying a mass of gas occupies 2 cubic meters at a temperature of 20 degrees Celsius and a pressure of 100 kilopascals. So here they're saying calculate the pressure calculate the pressure of the gas if the volume is increased to 5 cubic meters whilst the temperature remains constant. Okay, so you guys, when you're having this one, whenever you see that they are talking about a gas, right? Whenever you're dealing with gases, every time they mention the term gas, just know that whenever they mention the term gas, just know that all temperatures should be converted to kelvins. Okay. So here they're saying whatever mass, what, we are supposed to use the gas equation or the gas law equation, which is P1 of what? T1 is supposed to be equivalent to P2 V2 all of what? T2. Whereas P1 is the initial volume, P1 is the initial pressure, V1 is the initial volume, T1 is the what? Initial temperature. Then when it goes to 2 is the finals. So a mass of gas occupies 2,3. So meaning that our V1 is equivalent to what? 2 cubic meters at a temperature of T1 was given as 20 degrees Celsius. So we have to convert it to kelvins. How much is it going to be? (20°C to kelvins is how much, guys?
I don't remember how to convert that,
I forgot it formula.
So 0
I think
degrees.
degrees Celsius, it's 273 kelvins or something.
Yeah, 273 kelvins. So now you just have to add 273 plus 20, then you're going to get 293, right? So it's going to be 293 kelvins. Then, and the pressure of P1, we leave it as 100 kilopascals, guys. Don't change it to pascals because even the next one might be what they call it, kilopascals. Calculate the pressure if the gas, if the volume is increased to, so meaning that V2 is equals to what? 5 cubic meters. P2 is the one that you're looking for, right? Then T2, they say it remains constant at 20 degrees Celsius, which is equals to what? 293 kelvins, right? So if temperature is constant, let us cancel it out. There's no need for there. So you're just gonna have now 100 multiplied by 2 is equals to P2 multiplied by 5. Divide everything by 5, everything by 5. This 5 cancels here, meaning that 200 over 5 is equals to what? P2, meaning that our P2 will be equal to what? Is it 50? Go to what, guys? 200 over 5 is how much?
40.
40, no?
No, yes,
So it's going to be 40 kilopascals. Then you're done.
And then why should we divide by 5 there?
Yeah?
Why should we divide by 5?
Because remember, we are saying this is what P1, right? This is V1. This is now P2 and this is V2. So what is our V2? It's 5.
Oh, okay. So again, continue.
All right. So the last part that we're gonna do today is going to be the gas. The characteristic, gas equation. So this one, guys, is just a formula that you're supposed to use. So we know that it's going to be PV is equals to what? MRT, whereby P is equivalent to pressure in kilopascals, then V is equivalent to volume in cubic meters, M is equals to the mass, in kgs, then R is equals to the gas characteristic, okay guys, we have to go correct this one. Characteristic constant, then we are having T, which is the temperature in what? In kelvins. So the gas constant R will be in kilojoules per kg kelvins. Ne? So guys, don't use degrees Celsius because you're having what? Kelvins. Okay. Let's say we're having an equation here saying a cylinder contains 60 cubic meters of hydrogen gas at a pressure of 200 kilopascals and 23 degrees Celsius. Calculate the mass of the hydrogen if the gas constant hydrogen is 4150 joules per kg kelvins. Okay, so here we want to calculate the mass of the hydrogen, right? So here we're going to use the gas characteristic equation to say that PV is equals to what? MRT, right? So our pressure was given is 200 kilopascals. So we're going to say 200 multiplied by our volume now. The volume was given as 60, right? So we're going to multiply this by 60 is equals to M multiplied by our R, guys. You can see that this is joules, right? But this one was given in kilopascals. So joules to kilos, we have to divide. So this is going to be now 4,15 multiplied by our temperature. This was 23, right? So it's going to be now 23 plus 273. Okay, so meaning that 200 by 60 all over 4,15 multiplied by 23 plus 23 plus 273 is equals to the mass. How much do you get for your mass here, guys? I think we can do. How much are you gonna get if you punch your calculators?
Nine 9,768 kilograms. 768 kilograms.
Okay. So that's it, guys, for heat. We are done with chapter number 7. I don't know if you have any questions. If you still have energy, I can just try to get one question from the past exam papers, then we can do it together. But if you are tired, we can call it a day.
I think I have time for one more. I don't know about Risha.
Yeah, it's fine. We can do the last one.
Yeah. So no, we are done with the topic. When we are saying our last one, we're talking about the past exam papers. Let me just look for one.
Okay, cool.
TVET papers. Well, let me look for another account. Yeah. TVET papers. Okay. Here they are saying a copper ball has a volume of 0.685 cubic meters at a temperature of 289 kelvins, right? If the temperature rises to this one, calculate the increase in volume of the copper ball. Okay, so like what I was saying, guys, you see that in these cases now, we are not given the coefficients of linear expansion of copper, right? But if we go to the question paper now, if we go at the end here, you can see that they are saying the linear coefficient of expansion of copper is given here. It's 17, right? You see it, they are all given at the bottom here. So it's 17 times 10 to the power negative 6. So we are going to say linear coefficient of copper, let me just use red. Linear coefficient of copper is equals to 17 times what? 10 to the power of negative 6 per degrees Celsius. Okay. So calculate the increase in volume. So you know that increase in volume, that's volume final is equals to volume original multiplied by coefficient of friction is equals to volume original plus change in what? In volume, which is equals to volume original plus volume original multiplied by 3 coefficient of friction multiplied by what? Change in temperature. So V final will be equal to, the original volume was 0.685 plus open bracket 0.685 multiplied by 3 multiplied by, we got it as 17, right, times 10 to the power of negative 6 multiplied by, yeah, you have to be careful, guys, because these things are given in kelvins, right? But we need them to be in degrees Celsius because our coefficient of linear expansion is in what? Degrees Celsius. So 347 kelvins to degrees Celsius is how much?
3, it's gonna be 3, it's gonna minus 347 minus 273, then it's gonna be 0 degrees Celsius. And I
So
think
it's how much?
hey, I'm having difficulties.
I get 74 degrees.
74.
74.
Because you're going to say 347 minus 273.
This is.
So it's going to be 74 minus then 289 minus 273. 289 minus 273 is how much?
16.
16, right? What is your final volume, guys? If you punch your calculators.
I get 0.687.
0.687 cubic meters. Okay, let's just check the answers. Question 7. You see what they did here? Here they used kelvins, guys. Don't make the same mistake now. That's why your answers are a bit different, because you cannot combine the two, kelvins and what, and degrees Celsius. So they used 347 to 89, which is wrong. Then let's go to the second one. The volume of an unknown mass of a given gas at 150 degrees Celsius and the pressure of this one is this one. The gas constant is this one. Calculate the mass of the gas, right? So we know that here we're going to use the gas characteristic equation, whereby we know that PV is equals to what? MR. Let me just reduce my handwriting here. So it's going to be PV is equals to what? MRT. So they're saying the volume of a known gas at this and the pressure of, so they gave us 645 multiplied by 0.65 is equals to the mass multiplied by the gas constant. They gave us to be 5.18, but it's in joules, so we have to convert it to kilojoules, which is going to be 0.518 multiplied by our temperature. Temperature was given in degrees Celsius, but we are dealing with gases, so it's going to be 115 plus 273. So meaning that 645 multiplied by 0.65 all over 0.518 multiplied by 115 plus 273 is equals to the what? To the mass. How much do you get for your mass here, guys?
I'm getting a negative answer here.
Negative answer? How is that possible? Because remember, we're dividing. There's nothing subtractions here. This is plus.
Oh, yes, I get 0.208.
0.208. Sorry, this is mass, so they're going to be kgs. All right. So this one, guys, I want you guys now to try 8.3 and what? 8.4, because these ones, I think we did almost the same thing when we're doing our, what they call it, our examples. So we're going to do 8.3 and what? 8.4. Then when we are done, I think next, it's going to be next week, right? Because I think this one is the last class for this week, isn't it?
So,
yeah. So next week, I think you'll be having these answers. And also, guys, may you go through this HEAT. I'm going to send you guys your question papers for science so that you can also check if there are questions for you that you can actually start doing now.
okay.
All right. Is there any question, guys?
What question paper is that so that you can know?
Yeah?
Which question paper is that one?
This one was April 2021.
Sure.
Yeah.
Question 8.8.
So you're gonna do 8.3 and 8.4.
Sure.
Okay. Any question from lesson? Okay, so no one is having a question.
Sure.
Right, guys, so we can call it a day, right?
Yes, Tatenda.
All right, thank you for your time, guys. See you guys next week.
Stop it then.
Stop Tatenda.
Yeah.